You type a sentence, a futuristic spaceship navigating through the warped space-time near a black hole, and moments later, a full video appears, moving, flowing, lit perfectly, with camera motion, reflections, even physics that almost looks real. No actors, no cameras, no 3D software, just text turned into motion. This used to take a Hollywood VFX team weeks. Now, a model like Veo, Seedance, or Kling does it in minutes. But how? How does a machine go from a few words to thousands of consistent, photorealistic frames? Today, we're cracking open the black box of AI video generation, step by step. Modern video generators, Veo, Seedance, Kling, Runway, Sora, they all share the same DNA. And that DNA? It comes straight from image generation. If you watched our last video, you already know the trick. Diffusion. Start from pure noise. Train a model to clean it up, step by step, until the image appears. Video models do the exact same thing, but with one massive twist. They don't denoise a single frame. They denoise an entire volume, width, height, and time, all at once. And to make that work, every modern video model has to solve a few big problems. How do you keep frames consistent across time? How do you compress something as huge as video into something a model can actually handle? What architecture is powerful enough to learn motion? And how does your text prompt steer the whole thing? Each one of these hides a brilliant idea, so let's break them apart, one by one. Like I just said, video generation runs on the same core idea as image generation, diffusion. But if diffusion is still a fuzzy word for you, here's the 30-second version. You take a clean image, add noise step by step until it's pure static, then you train a neural network to walk it backwards, predict the noise, subtract it, repeat, and eventually a clean image appears out of the chaos. That's it. That's the whole trick. We covered it in depth in the last video, links in the description. Now, here's the part that matters for today. Video generation takes this exact same idea and stretches it across time. Same denoising, same math, just a much, much bigger canvas. And that bigger canvas brings a whole new problem. That problem? Time. Generating one good image is already hard, but a video at 24 frames per second? A 5-second clip is 120 frames, and those frames can't be random. They need to be consistent. The same character, the same outfit, the same lighting, the same reflections in the same puddle, frame after frame after frame. This is the fundamental challenge of video generation. Temporal consistency. Early attempts, they generated each frame independently. And the results? Well, they flickered like a broken neon sign. Faces morphed, backgrounds wobbled, objects teleported. The breakthrough? Stop thinking of video as a sequence of images. Start thinking of it as a single three-dimensional object, a block of pixels, with time as the third axis. This is the key insight behind most modern video models. A video isn't just frames, it's a space-time volume, a cube where two axes are space and one axis is time. The model chops this cube into small three-dimensional patches, little bricks that span a few pixels wide, a few pixels tall, and a few frames deep. Each brick is called a spacetime patch, or a video token. These patches become the basic unit the model works with, just like words are the basic unit for language models. And here's the magic. By treating space and time the same way, the model naturally learns motion. It learns that pixels in nearby frames are usually similar. It learns how things move, how objects deform, how light shifts. Motion isn't a special add-on. It's baked into the representation from the very start. Spacetime patches are powerful, but run them on raw pixels? It's just way too expensive. Imagine this, a 5-second clip at 1280 by 720 resolution, 24 frames per second? That's over 100 million pixel values. So before any diffusion happens, the video gets squeezed into a much smaller latent space by a three-dimensional variational autoencoder. A regular image VAE compresses width and height. A video VAE compresses width, height, and time. That huge raw video becomes a tiny latent volume, typically shrunk by around 8 times in space, and 4 times or more in time. That's hundreds of times less data to process. Same content, same motion, just packed into a much more compact form. All the diffusion happens in this compressed latent, making generation actually feasible. Only at the very end does the decoder expand it back into the full video you see. Okay, now we know diffusion happens in a compressed latent space, but what's actually doing the denoising? In our image generation video, we talked about the U-net, a U-shaped convolutional network trained to handle the denoising. Now, for video, most modern systems have switched to a different architecture, the Diffusion Transformer, or DIT. Here's why. Transformers are the same architecture that powers ChatGPT, Claude, and other large language models. They're built on attention, the ability to look at every token and decide which other tokens matter. For video, this is perfect. A patch in frame 50 can directly attend to a patch in frame 1 and learn that they're the same character, in the same shirt, with the same lighting. That's how the model maintains consistency across long sequences. And there's another huge bonus. Transformers scale, make them bigger, feed them more data, and they just keep getting better. That's why video quality has exploded over the past 2 years. Bigger DATs, more spacetime patches, more training compute. So we've got a powerful architecture for denoising, but how does it know what video to actually generate? Just like image models, your text prompt gets encoded into a high-dimensional vector. We call it a text embedding. Then that text embedding gets injected into every layer of the diffusion transformer through cross-attention. At each step, every spacetime patch asks itself, what should I look like given this prompt? And the prompt has answers. For example, take our prompt from earlier. The word spaceship pulls the main object into shape. Black hole controls the lighting, the shadows, the gravitational distortion. Warped spacetime bends the starfield and adds lensing across the whole scene. And navigating. That one guides the direction of motion across time. On top of that, classifier-free guidance amplifies the effect of your text, making the output more vivid and more prompt-faithful. Here's a critical detail. The better the captions used during training, the better the model follows your prompt. That's why the top labs train their own captioning models that write incredibly detailed descriptions for every training video. And that is why modern systems follow complex prompts so well. Okay, let's watch it generate. We start with a 3-dimensional volume of pure random noise, total static, in space and time. The model considers your text prompt and predicts what noise to subtract across the entire volume, all at once. After one pass, slightly less noisy. By step 10, vague blobs that flicker and shift. Step 20, recognizable shapes, and they start moving coherently. Step 30, the spaceship takes form. The stars bend around the black hole. Space-time warps and glows. And at the final step, a clean, latent volume that the VAE decodes into thousands of consistent, photorealistic frames. The whole denoising process happens to the entire video at once. Not frame by frame, not left to right, all of it together. That's why the motion looks so natural. Every frame is generated, with full knowledge of every other frame. But here's the catch. Generating the whole video at once works great for a few seconds. But what about longer videos? A minute? 5 minutes? Even with latent compression, only a limited number of frames can fit into a single pass. So modern models use clever tricks. Some, like Sora, extend videos by conditioning new frames on the last few frames of the previous chunk, sliding window style. Others train explicitly to fill in the middle. Given the first and last frame, generate everything between. And the newest systems, like VO, can even generate matching audio and dialogue alongside the video. Each new generation pushes the boundary on length, resolution, and control. All right, we've covered a lot so far. Let's tie it all together. Your text becomes a meaning vector, the text embedding. It guides the entire generation, but before generation can even start, we need a place to generate in. A video VAE defines that place, a tiny, 3-dimensional latent space way smaller than raw pixels. Inside that space, the model works with spacetime patches, the basic unit of video tokens. A diffusion transformer denoises a whole volume of patches at once, guided by your text embedding through cross-attention. And finally, the decoder expands the clean latent back into a moving, breathing video. It's not magic. It's the same elegant diffusion idea, just stretched across time. Add transformers, add scale, add great training data, and suddenly, machines can dream in motion. That's it for today. Like and subscribe so you don't miss more AI deep dives. See you in the next one.